So, okay guys, so here. So we have a new lesson which is the gravity. So aside from gravity, we will be discussing another lesson for today, which is waves. So today we will be discussing two, two lessons. First one will be gravity and the second one will be waves. Okay, so let's start first with gravity. Okay, yes. Okay, so gravity. So this will not be only focused on the lesson of gravity, but also with the periodic motion. Okay, so yan. So we will be using here the Newton's law of universal gravitation. So this will be a little different from the gravity that we have discussed previously, but this gravity will pertain to the gravity uh, using the planets, the sun, and the moon, and also the satellites orbiting the Earth. Okay, so that is the gravity that we will be defining or we will be discussing for today. So gravity is the force by which a body draws objects, particles, or other body towards its center. So normally we can observe gravity here on Earth for everything we throw up must come down. So but the difference about this gravity is this is a gravity that holds two bodies. Okay, so two bodies or multiple bodies within its reach. Okay, so this is not a gravity that when you throw something, it will comes down. So this gravity is the pulling of two objects near to its core. So yes, this have the same principle that we have in the gravity that everything you throw must come down. So this gravity is a little different. So we will be discovering that gravity here. Okay, so we have here the Newton's law of universal gravitation. So the Newton's law of universal gravitation states that two bodies in space pull on each other with a force proportional to the mass and distance between them. So two bodies in space. So that is the keyword. In space, pull on each other with a force proportional to their masses and distance between them. Okay, so in mathematical state or in mathematical uh, equation, so it is known as the gravitational force, which is F. The force that acts on two objects is the attraction of the masses of mass 1 and mass 2. Okay, so directly proportional to the product of the mass of two bodies and inversely proportional to the square of the distance between them. So we will be having here F is directly proportional to the masses, product of the masses, and inversely proportional to the square of the distance between them. Okay, so uh, this is the second. No, not the second. So this is the mathematical equation, but this is not yet the working formula for since we have a proportionality sign, and we will be going to make this a working equation in which we will be using equal sign instead of proportionality sign. Okay, so with this we will be exchanging our proportionality sign to our equal, but we have a constant. So in here we have a constant of g, which is known as gravitational constant. So this gravitational constant has a unit of 6.67 times 10 raised to negative 11. Remember that, negative 11 cubic meter per kilogram multiplied to second square. Or in other terms, we will be having Newton square meter per kilogram. Okay, so Newton per square meter Newton square meter per kilogram. Okay, so I hope you got this one, guys. Okay, so we have gravitational field and field strength. So normally when we talk about gravitational field, this is where gravity acts on. Okay, so the gravity here is acting, and the other one is also reacting to the other object. So both of these have a gravity, both of them, but the force that is exerted is varying, since the greater mass has the greater force, and the lesser mass has a lesser force. But those force are enough to pull each other, but not collide. Okay, but they will not be colliding to each other. Okay, so we have a formula here of F is equals to G, gravitational constant, multiplied to mass 1, mass 2, all over r squared. So we have here, let's substitute, or let's cross multiply. We just cross multiply mass 2 to our denominator of our F. Okay, so force is divided by MO, or test mass, in which we can determine the gravitational value in the equation gm1 all over r squared is equal to G, or gravitational magnitude of the field. So it has a unit of meter per second squared. To rewrite the equation, we have G is equivalent to our F is equals F over MO. Okay, yan. So yan, we just rewrote this from here, and that one is this one. Okay, so yeah, so we have here the test mass MO, and our G here is what we call the gravitational magnitude of the field. Okay, so that is just how we will going to test um, our gravity. Okay, so yeah, so here's the example of our gravity pulling on both objects. So we have here the Earth with the mass, and its gravity is pulling the satellite, while the satellite is also pulling on the Earth. But as you can see, none of them are colliding, since they have enough force away to each other, that they just orbit around and not collide to each other. Okay, so here's a video clip of the example of uh, the swirling, or the orbit of satellite on the Earth. Okay, so let's watch this one, guys. So here we have the green arrow, which indicates the velocity of our smaller mass, the one that orbits around our main object, which is the Earth. And we have here the gravitational force towards to each other, guys, as you can see here and here. So both of them are towards to each other, because if they are pointing on the other side, on the other end, it will both of them will just part ways. But since they are pulling on each other, that gravitational force is pulling on each other, and they are not colliding, but they are exerting enough force to hold each other. Okay, so this white line is the pathway on where our satellite is orbiting around the Earth. Okay, so here is another example, another clip. This is the moon and the Earth. Okay, so let's see what's gonna happen in this video. I guess this video will be adjusted. The mass of the Earth will be adjusted. So we will see how the moon will react to it. once it is adjusted. Yun, okay. So the Earth size was adjusted to 1.5. So as you can see, the direction and the orbit of the moon adjusted. So mas lumakas yung hatak ng gravity sa moon. And also niliitan naman natin yung mass ng moon. So ibig sabihin mas maliit yung uh, force na naiibigay ng moon. And there is also a slight change. So what will happen if we overexert the force? Okay, so there is a collision. So there is a collision if we have overexerted the force or the mass of our objects. So that the object that is being rotated on is being adjusted to its maximum. And as you can see, guys, as you can see that our orbiting object or orbiting planet, orbiting moon on the Earth have collided, and there, if there will be collision, there will be catastrophe. There will be catastrophe, guys. Okay. So next is we have here another example, another video clip on where we can see the orbit of our moon, not to our Earth, and there is also a change in Earth's mass, and then there is a sudden return of uh, return of value of our planet's mass. So as you can see, our object rotating the Earth is the moon that rotates on the Earth is being thrown off. So it's being thrown off, and as you can see, there is an elliptical shape, of pathway of our moon away from the Earth. Okay, so that is what happened if you suddenly adjusted the mass of the Earth and then suddenly change it back to its original state. So meaning, what happens there is that when you adjusted the mass of the Earth, it becomes bigger. When it became bigger, the mass of the gravity also became bigger. That's why there is a short distance here between the moon and the Earth. And when we suddenly change it back, there is a wider gap. There is a wider gap of the moon and the Earth. Okay? Since there is a wider gap, so meaning the value of our gravity or the force in here in this location, which there is a minimal space between the moon and the Earth, and then this and in this space, that the distance between the moon and the Earth has a great distance, for the reason that in this area, the force is greater than this force. Okay, so that is the explanation on why there is a great distance between the moon and the Earth. Okay, so let's have this another example. Yeah, so let's play this one. Okay. So as you can see, guys, from this point of view, there is a perpendicularity between the direction of the gravity and the direction of the velocity. Okay, so this is just the same video. Okay, so that's it for the video presentations. So we have here gravitational potential energy. So the gravitational potential energy from our previous lesson, it is the gravity that is being yet to be produced. Okay, so gravity that is being yet to be produced, and that is due to the to the gravity per se of our object. Okay, so gravitational potential is known to be an energy transferred or work at a position per unit mass that would be needed to move an object to a position from a fixed reference point. For the gravitational potential energy, it is the work done against gravity to bring up a mass to a given point in field or space. Okay, so we have here the gravitational potential with the unit of joules per kilogram. So we have a formula of V is equals to negative. It is always negative. So this is included also. G M1, gravitational constant times mass all over the distance. Okay, so and we have universal gravitational potential energy, which is in a unit of joules na. So since it is potential, we have joules per kilogram, but if it is energy, we have joules. Okay. So same values we just promoted, or we just got a level up from gravitational potential, which is V, to gravitational potential energy. Okay, so we have just V and U. The formula is the same. We just adjusted our usage to it. Okay, so escape velocity. So escape velocity is the minimum magnitude of velocity to escape or free the subject from the gravitational attraction of a particular body or planet. In a mathematical note, if the gravitational potential energy is equal to the kinetic energy of an escaping object, then the absence of uh, frictional resistance could mean the escape from attraction. So we have here a formula of 1 half m VE squared, which is equivalent to G M1 M2 all over R. So we have here the velocity, escape velocity, which is meter per second, and gravitational constant, cubic mass all over kilogram times second square. So we have mass in kilograms and distance in meters. So manipulating this formula, so transferring or cross multiplying 2 in here, and we can cancel one of the masses, which is visible to our two objects. Cancel this mass and the other mass, and what we have, VE squared and GM1 all over R. So since this is square, we might ought to put a square in here. So meron tayong 2 dito. Cancel natin to, and this will leave us a formula of velocity of escape is equivalent to square root of 2 gravitational constant multiplied to our mass 1 all over R. So, included yung R natin sa ating square root. Okay? So, R is included in our square root symbol or square root sign. Okay, so I hope guys you get this formula. Okay, so please copy this one. Okay, so let's continue. Okay. Yes. Okay. So here is an example of what is an escape velocity. Okay. So let's watch this video. So it's a normal thing that the moon is orbiting our Earth, but suddenly there is a change in planet's mass, and it will happen next. Okay, so as you can see, guys, there is a change in mass of our Earth, and there is also a sudden. Okay, so let's try to rewatch it. So there is a change a while ago. There is a change of mass on our Earth, and then it suddenly got back. But before it got back to its original mass, the moon returns its rotation within the Earth's sphere pa rin. Okay. And there is a change, and then yeah, there is another change, but this time there are no more moon, and the escape velocity has it figured out its way out. It figured out its way out uh, for our for our moon to escape the gravitational binding between the moon and the Earth. So here in this picture, you can see that the velocity is going away from our Earth, even though there is a gravitational pull between the two. Even though there is a gravitational between the two, the velocity has a greater value, greater force exerted, so that there is enough velocity, escape velocity, to pull the moon away from our Earth. So in here, yeah, so as you can see, the velocity is in a greater position, which is it can easily pull the moon away from the Earth. As you can see, the velocity a while ago, or the gravitational force is greater than this arrow, but but suddenly but suddenly it got smaller, or it got shorter. So meaning the force, or the gravity between these two, the moon and the Earth, has shortening, or suddenly disappearing. Okay, so that is our escape velocity. Okay, so satellite and planetary motion in circular orbit. So in space, satellite moves around the Earth, and so as the Earth moves around the Sun in an orbital pattern. So not only satellites move around the Earth, but also the Moon. So consider body of mass in motion, in the speed in area of mass of a body. For example, the structure might be a sun and a planet revolving around it. Assuming that the body of that massive body of mass is at rest in an inertial orientation frame, then the total mechanical energy of the two-body system of the sun of a kinetic energy and potential energy. So we have here the value, the formula of our E, which is our total mechanical energy, and we have here kinetic energy plus the universal the gravitational potential energy. So we have here 1/2 mv squared plus negative. So a while ago, I just told you that this negative is functional. Okay, so G, M, and N all over R. So we have here the total mechanical energy J. We have M, mass of the bigger object, and mass of the smaller object in both kilograms. So we have here R, distance between the objects in meters. We have V as our velocity, meters per second, and gravitational constant of 6.67 times 10 raised to negative 11 cubic meter. Okay, cubic meter all over kilogram second square. So always remember this formula, and this might be used in our examination. Okay, so I'll give you time to copy this one, guys. Okay, so let's move on to our next slide. So, okay, so here is another video, satellite orbit around the Earth. Okay, so let's just appreciate the rotation of our satellite around the Earth. Okay, so this is a mixture of our kinetic energy and gravitational potential energy. Okay, so energy, conservation of energy, which is we have here kinetic energy initial plus gravitational potential. Gravitational potential energy initial is equivalent to final of kinetic and uh, gravitational potential energy. So we have formulas here, which is 1/2 mv squared. So for our kinetic energy, and negative g, greater mass and smaller mass all over r for our gravitational potential energy. So we have here Kepler's laws of planetary motion. So Kepler's three laws of planetary motion can be explained and stated as follows. So first one is the pathway of the planet's orbit around the sun is in elliptical in shape. So with the sun at one focus. So we will be having a video for that. And an imaginary line drawn from the center of the sun to the center of the planet will sweep out equal areas at equal time. So equal areas and equal time. So the square of the periods of any two planet is equal to the cubes of the semi-major axis of its orbit. So since it is elliptical, so there will be major and minor axis. Okay, so first we have here the pathway of the planet's orbit around the sun is in elliptical in shape with the sun at one focus. For example, here is our sun and the other planet is orbiting around our sun. Okay, so here is the video for that. So in elliptical in shape. So this is the Earth elliptical in shape to our sun's focus. And as you can see, guys, so this is not just happening to our Earth but also in other planets. So elliptical din siya. If it is elliptical, then other planets will be elliptical too. Okay? So that is our first Kepler's law of planetary motion. So the pathway of the planet's orbit around the sun is in elliptical in shape with the sun at one focus. So for the next is an imaginary line drawn from the center of the sun to the center of the planet will sweep out equal areas at equal time. So here is the imaginary line that Kepler is talking about, sweeping this entire area equal areas at equal time. Equal areas and equal time. Okay, so let's see. So, yan. So, okay. So that is the area sweeping. Equal time din also. So equal time, equal area that is being exerted here in our uh, motion or the movement of our planet, and with sun at its focus. Okay? So the next is the square of the periods of any two planet is equal to the cubes of the semi-major axis of its orbit. Okay, so for example, here we have an example of our problems here. So first example is the gravitational force 3.884 times 10 raised to 8 meter is the known distance between the moon and the earth. So as you can see, if you're just going to think about it, it is a little short. It is just multiplied to 8. But our 8 is, um, we have kilo, we have giga, and we have kilo, we have mega, and we have giga. So 9 is our giga, and it's just a little shy to be a giga. So this means that this is a thousand of 10,000 of kilometers. So this is far. Okay. So between the moon and the Earth. So if the Earth's mass is 6.00 times 10 raised to 24 kilogram, and the moon's mass is 7.4 times 10 raised to 22 kilograms. Solve for the gravitational force each exert to each other. So let's try to solve for this. Okay. So yeah. So let's try to solve this one. Okay, so here goes. So we have here given r, or the radius, or the distance between the two objects, the two masses, which is 3.84 times 10 raised to 8 meters, and mass of the Earth, which is 6.00 times 10 raised to 24 kilograms, and mass of the Moon, which is 7.4 times 10 raised to 22 kilograms. So using the formula of F is equals to G, gravitational constant, mass 1, mass 2 all over r squared, we can have the force of 2.01 times 10 raised to 20. So let's try to solve this one. So here goes. So we have gravitational constant, which is 6.67 times 10 raised to negative 11. And we have here 7.4 times 10 22 for for our moon, and 6.00, or simply 6 times 10 raised to 24. So all of these will be divided to 3.84 times 10 to 8, which is squared. Okay, square equal of 2.01 times 10 raised to 20 Newton. So our value here is correct. Okay, so that is, for example, one, which is gravitational force. So let's move on to our next, which is gravitational potential and gravitational potential energy. So EXE, an assumed planet in the outer space, has a mass of 5.5 times 10 raised to 23 kilograms and the radius of 3.3 times 10 raised to 6 meters. So a 60-kilogram satellite is to be propelled vertically from its surface if the satellite is propelled within initial energy of 5.5 times 10 raised to 9 joules. Solve for the kinetic energy when it is 8 times 10 raised to 6 meters from the core of planet X. So please try to solve this one, guys. And balik tayo once na you have ideas or you have answers for this. Okay, so see you. So, okay. So we have here values of our given here. So we have mass of our planet EXE, 5.5 times 10 raised to 23 kilograms. The radius of our EXE, which is 3.3 times 10 raised to 6 meters. And we have kinetic energy, uh, 5.5 times 10 raised to 9 joules, and radius of 8.0 times 10 raised to 6. So mass of the satellite 60 kilograms. So we have here gravitational potential and potential energy. So we have here our formula, which is KE. KEI uh, KE initial plus gravitational potential initial, which is equivalent to KEF plus uh, our UF, or our gravitational potential find. So substituting the values that we have here 5.5 times 10 raised to 9 joules minus 6.6 times 10, 6.6 times 10 raised to uh, 11 for our constant, which is cubic meter per kilogram second square. Okay. And 5.5 raised to 23 kilogram times 60 kilograms. So as you can see, we use the longer version, or we expounded everything here from the kinetic energy to our universal potential energy. And for this, we have the kinetic energy final of 4.558 times 10 raised to 9 joules. Okay? So next, we have the escape velocity. Let's try to solve for this. Solve for the escape velocity of Earth, for it has a mass of 6 times 10 raised to 24 kilogram, and radius of 6.35 times 10 raised to 6 meters. Okay, so let's try to solve this one. Okay, yes. Okay, so we have here a given of mass of the Earth, which is 6 times 10 raised to 24 kilograms, and the radius of the Earth, which is 6.35 times 10 raised to 6 meters. So formula V escape is equivalent to square root of 2g mass 1 all over r. So substituting the values here, we have value of 11.22, 11,227.1 meter per second. So let's try to solve this one. Okay. Yeah. Okay. So we have 2 times 2 times. Nope, 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 nope. Syntax error. Let's go back. 2 times 6.67 times 10 raised to negative 11. And another one, which is 6 times 10 raised to 24. The radius of 6.35 times 10 raised to 6. So, okay, so the answer is 11,227.07 or 1 meter per second. So here you can see that we have the exact value. Okay, so moving on to the next. So we have here the waves. So we have here waves. Physics note, waves. Okay, so waves, mechanical waves are waves normally heard in metals clanging, vibrating strings, water waves, and many more. So the reason they are called mechanical waves is because they have their own medium that can be either in solid, liquid, or gases. Okay, so properties of waves, we have amplitude. It is the height of the waves and measured in meters. Wavelength, it is the distance between the adjacent crest measured in meters. And we have the period, the time it takes for a complete wave to pass a certain point, measured in seconds. And frequency, the number of complete waves that pass through a point in 1 second, measured in inverse period or hertz. Speed, the horizontal speed of the point on a wave as it spreads, measured in meters per second. Okay, so here are the properties of the waves, and here is the actual picture of a wave. So we have here the crest. We have here the crest from our reference line up to the maximum curve in our wave travel. Okay, so we have here wavelength. We have the wavelength, which is from our starting point and down to our first passing and going upward. So if our wave repeats itself, then we have one complete wavelength. So if it is not yet repeating itself, that is not a complete wave. So the repeatance of itself is from going to our crest to our throw and going back to our reference line. So that is one complete wavelength. So the height is what we call the amplitude. So crest is the upper curve and throw is the lower curve. So the amplitude is the height of our curve of our crest and our throw. Okay? So yeah, so as you can see, we have two complete wavelength and half of it. Okay, so let's move on to our types of mechanical waves. We have the longitudinal and we have the transverse. So waves in which the displacement of the medium is in the same direction as or the opposite direction of propagation of the waves. Another thing about this wave is consists of compression and refraction. So we have here the longitudinal waves. So these are commonly seen in our radios, but this cannot be. This is a little difficult to interpret or to read from the transverse. Okay, so we have here the compression and we have the refraction. So the compression is the shortened distance of our um, wavelength, and we have here the refraction, which is the stretch, just like the spring, and then there is also another compression. So this is what we call the longitudinal waves, and this one is what we call the transverse waves. So these are the most commonly known waves that we can see or we can be applied in our real life situations. Okay, so we have here one example, this video of our transverse wave. So, yan, as you can see, there is our throw, and then there is a crest, and as you can see, it is completely um, repeating itself, up, down, up, down, and as you can see, that is a complete wavelength. Okay, so yeah. After it completed itself, its sound or its waves, it will always go back to its original position, which is this level. Okay, so as you can see, water level, this is measured through the use of water. Okay, so let's move on to the next, which is the sound and sound intensity. So sound is a vibration that spreads as an auditory wave through a spread medium such as gas, liquid, and solid. So sound intensity is known as acoustic intensity, defined as the power carried by sound waves per unit area in a direction perpendicular to that area with a unit of watts per unit area. So we have two types of interference. We have the constructive and destructive interference. So if they are both on the same wavelength in the same direction, we will be having a much larger wave. So this one is what we call the constructive. Okay, so constructive from the word itself, to construct, piling things up, piling wavelength, another wavelength, and another wavelength. So that is what we construct. So if they are both on the same wavelength, they will be riding each other. And once they ride each other, they will produce a much greater value of our interference. While on our destructive, so from the word itself, destructive, they negate each other. So this one is, the first one is the crest, then the throw, and then the crest again. Now this one is a throw, crest, and throw. So since they are on the same value but different in directions, they are just going to negate each other. So nothing will be happening in here. So it's either will be masakit sa tenga, no harmony at all, or it's just plain sound production. Okay? So we have very different types of videos that I'll be showing you. So this one is the first video of waves produced by sound. So we have graph, play tone, and we can see the movement of our particles and waves. So in here we can see the pattern of our waves. So it's quite constructive but also quite destructive. But as you can see, it is basically constructive since they have the same direction, but there is only an interval, a minimal interval of their waves. Okay. Okay, so as you can see, particles are moving whenever they were hit by sound waves, and once the wave subsided, they will be back to their original location. So as you can see, the waves is still clanging in here, and it is flowing. Okay, so let's go back to this one and I'll be showing you something pa. Okay. So in here, as you can see, there's a large wave on the start of our the start of our waves, and as you can see, it is gradually flattening. So this one has a bigger value of our waves, and in here we have a smaller up to none. So there is also what you call the ripple effect, that whenever the waves hit the particles and the objects, or the waves are slowly disappearing. So they are slowly flattening the curve. Okay, so sana ganun din talaga sa COVID, flattening the curve. Okay, so another for if that is a sound now, water cannot be missed. Okay, so we have here also, we have graph, and yep, same goes for our sound. It started with a greater value of our magnitude or amplitude, and it is gradually flattening also. And as you can see, we adjusted, and there's a reading of slightly destructive but still constructive pa din. Okay, still constructive. Okay, so next is we have also light. So as you can see, guys, here, light also emits sound waves. So as you can see here, turquoise then adjusted to our red light, and what happens? So yeah, so there is a uh, change in our graph electric field, and adjusted to violet. What will happen? Okay, so uh, this is a visible destructive interference. So it's a minimal destructive, but aside from a while back, we can see that the constructive waves are a little minimal. The destructive waves are a little minimal, but this one is a great, and as you can see, it is really going on a different directions. Okay, so and as you can see, um, the movement of the waves is greatly affected when light color lights are being changed. Okay, so let's try to look at this. The first is the turquoise. As you can see, it's fast, but it's purely constructive. Okay, it's purely constructive. While when we switch to the red light, it's a little destructive, but constructive as well. But as you can see, it's a little slower than our turquoise, slow moving than our turquoise. But when we switch to the violet or the purple color, as you can see, the wavelengths are going bananas. It's fast. It's visible yung ating destructive. Okay, so we have here the green, which is, yes, this one is purely constructive. Okay, so both of the wavelengths are going on the same directions. Okay, so we have identified here the constructive and the destructive. We have seen in here through the use of the light. So even light can produce wavelengths. Okay, so I hope, guys, that this lesson is new to you. Okay, so we have here the next thing on strings. Okay, so on strings, so this one is an oscillating source, and as you can see, we have here the fixed end of our strings. Fixed end. You can also try this one uh, in our homes. So loose end, what will happen? So yes, it is freely moving, but as you can see, there is also wave going backwards from our source. So when it's moving in here, so hindi maaaring wala ding may bibigay yung loose end natin. And now we have no end, and as you can see, it is just freely flowing and no movement or no waves are going back that can heighten the value of our frequency. Okay? So that's it, guys. We've reached the end of our discussion. So I hope, guys, you have uh, gathered some new information about this lesson. And if you have questions, guys, you're free to ask and you are free to raise your hands if you have uh, any confusions about this lesson. So so that's it, guys. So I hope, guys, you have a great time listening to our lesson for today. And if you have questions, queries will be entertained. And if you don't have any, so I'll be seeing you guys on our examination. So thank you, guys. God bless. Peace out.